Okay, this is lecture 26 of our um, VLSI devices course. So the last one, and it's the Korean Memorial Day today. So our lecture room is closed, so I cannot access to the lecture room. So that's the reason why I'm currently recording in my office room. Okay, so maybe there can be some troubles, but let me just try. The final lecture, lecture 26, will be devoted to the double gate, but not entire model for double gate MOSFET, but I will just consider the double gate MOS structure. So just simply calculate the charge density due to electron, inverted electron, as a function of the gate source quantity. Or, mm, or no. Mm, so in this case, this is the function of a gate voltage is done by considering MOS equation, and I will just consider instead of this one, just a function of, for example, surface potential. So you will see that actually in the case of our double gate MOSFET, actually inversion charge density is not a sole function of surface potential, but also we need the information about another point at the midpoint. So anyway, I will try to deliver this discussion in today's lecture, lecture 26. Okay, so let's just quickly go to our lecture material. In order to derive the double-gate MOSFET, we adopt some approximations. One is here, no substrate doping. So simply speaking, Na equal to 0. And also, we adopt fully depleted channel approximation. So hole density is also neglected. So in this case, we neglect total density, hole density, and the net charge density inside our device is just solely given as minus 2 times n. Only electrons uh, are contributing to the net charge density. Then the Poisson equation can be simply written as this form. Of course, we must write down many contributions from holes and doping density in this right-hand side. However, nothing occurs here and only electronic contribution. Uh, so now please have a look at this expression. This is given by just the coefficient and intrinsic carrier density exponential of electrostatic potential. So now you understand this electrostatic potential is no longer referenced to the x equal to infinity. That was used throughout our planar MOS discussion. However, in the case of this double gate, we just use the normal conventional one for this electrostatic potential. That's the reason why here we have an I. And here we have, of course, electron quasi-Fermi potential. So this is corresponding to this quantity. However, in this discussion, we will just treat it as number 0. Of course, when we go to the MOS field effect transistor, then depending on the position, we can have position dependent uh, electron quasi-Fermi potential, but uh, currently we are just considering MOS system, so it's okay. So the structure is assumed in that way. But due to the mirror symmetry, we just consider the origin as a midpoint and the entire silicon thickness is given as T and it is divided by 2 because this is positive half and negative half. Of course, we assume the mirror symmetry. So um, we will talk about how can we express some quantitative in this semiconductor region with representative potential values and some important points. We find that actually important points are this is an important point and this is an important point. Of course, this one is also important, but due to the mirror symmetry, once we know the quantity at this point, then it can be just a mirror. Okay. Then how can we obtain the expression for our double gate MOSFET? So please recall the procedure we have done in our planar MOSFET analysis case. At the time, we multiply the weighting factor corresponding to the electric field. After that, by integrating this modified permutation, we were able to get the square of surface electric field. We will just to repeat this procedure once again exactly for our double gate MOSFET. So in this case, if we just multiply this one, then equal from that, then now we will have d5 over dx and d5 over dx. And it is integrated from 0 to a certain position x for y, just to assume that x is equal to positive. So means that we wanted to do some integration from this initial point to up to at a certain value x. Of course, eventually we will go to this half thickness, but in general we can start anywhere. So this is x or this can be x. Okay, so in this case, this technique is already known to you because when you take its derivative, we will have 2 times the phi over the x and times 1/7 derivative of the phi over this. They are cancelled, and this is just the left-hand side of our quantification multiplied with this weighting factor. So we can recover its original form. And now, by integrating from 0 to x, then actually we have to evaluate uh, this quantity, half of square electric field at twice, at x point and at 0 point. However, what is this x equal to 0? This is corresponding to the mirror symmetric point here. So potential is always mirror symmetric. It means that at x equal to 0, our d5 over dx must vanish. So that's the reason why, although we have to calculate the upper limit and lower limit of this integrand, but this can be gone, and now we only have square of electric field evaluated at a certain x point. And after that, this one can be easily integrated because we are now performing the x integral. So dx can be cancelled out, and we can just integrate this integral with respect to phi variable. So that is shown here. Of course, this is upper limit of our integration and lower limit of our integration. And since lower limit is corresponding to x equal to 0, that's the reason why we need the potential at x equal to 0. What is it? Do we have any idea about this value? So actually not. Uh, Please think about the case in our planar MOSFET. If we follow the planar MOSFET case, quite similarly, we have the expression like phi equal to infinity. However, in this case, the condition at x equal to infinity can be easily obtained since we have a certain p-type acceptor density, and from that one we can easily recover this quantity. However, in the case of our double gate MOSFET, there is no guarantee that this value is fixed to a certain given number. So this number phi at x equal to 0 should be regarded as another unknown variable. So, well, we will just keep it here. Then, simply speaking, now we have square electric field, and this electric field can be simply written as this form. So, since we are currently considering positive x value, of course, if we consider negative x value, we have to introduce a negative sign, but I will just skip this negative part. Yes, so please note that this x value is x potential at any arbitrary x value. Also, this is evaluated at any arbitrary x value. So this is the expression for electric field. Okay, then in order to solve the MOS equation, we need the surface electric field. So yes, we need that information because the surface electric field is converted to the charge density. And yes, so how can you calculate this surface electric field? By just applying x equal to half of the thickness, now we have this good expression. But point is, previously, when we consider planar MOSFET, then there occurs the term corresponding to surface potential. So, uh, surface electric field can be written as a function of surface potential only. However, now in the case of this double gate MOSFET, mm, now you can see that there are two quantities, surface potential and the potential at the midpoint. So in the planar MOSFET, the surface field was a function of just the difference between surface potential and the potential at each substrate. So we just took it as a surface potential and introduced some modifications in the coefficients. But now we just keep this convention. And now it is a function of surface potential and midpoint potential. Well, then when we include this expression, so now there is one equation, MOS equation, but it is a function of surface potential and midpoint potential. So this problem, this equation cannot be uniquely solved because we have two unknown variables and only one equation. So simply speaking, in order to solve this equation uniquely, then we need a second equation. So how can we introduce this second equation? That is done in this slide. So now integrate it once again. So now we can just introduce an intermediate variable and just change it from our potential variable to this transformed variable. And since this is just expressed as exponential function, so this one is just dimensionless or quantity. And of course, by taking this exponent, it is always larger than zero. And also, please think about this one. Here we have the difference between potential at any point and midpoint potential, and we assume that so x equal to from x equal to 0, potential is potential, not energy. The potential is going up. So this can be regarded as just a non-negative number. So means that this one is non-positive number. So always this y variable is lower than or equal to 1. Okay, so that is shown here. And at x equal to 0, of course, at x equal to 0, then y becomes y naught. So this one becomes 0. So we have y equal to 1. This is quite understandable. And now, using this new variable, y variable, then now we can write down our um, electric field expression in this way. Well, you can just check it by applying this variable transformation. And now you can understand this is just a given number and this is a given number, and we have square root of 1 minus square y. So we can just send it here. Then we must make some integration of this quantity. Yes, and fortunately, its form is known. This one gives us arc sine, so inverse function of sine function. So that's the reason why now we have arc sine function. This is inverse because sine function at y. What is y? This is the y evaluated at any arbitrary x value. And what is this? In this case, also we have to calculate y evaluated at x equal to 0. But at x equal to 0, y becomes 1, and arc sine means that what is the angle to generate sine function equal to 1. So this one becomes just half of pi. So this is corresponding to the lower limit of our integration. And that was the left hand side. You know, this part this part is obtained by just integrating this and this, and the remaining part should be integrated. However, this is just a constant over a position x. So, simply speaking, we have just a constant, the same constant here, and x. Of course, we have to calculate this quantity, x over 0 to x. This one simply becomes x. So there is no other approximation. So simply speaking, now this one can be gone to this right hand side, and taking the inverse of this arcsine function. So now we can say that y equals to sine half pi minus blah blah blah, and it can be written as cosine of this input argument, and we are just looking at this expression. And what was the y variable? So we just introduce it here, so it is simply given as minus ABT over Q and phi minus phi naught. So if we consider this one, then we can just take a log over this expression. Then, simply speaking, now we have this form. Okay, so difference between the midpoint potential and potential at any arbitrary position is simply given as seemingly quite complicated, but now we have a given analytic exact expression. And since we are interested in the relation between phi s and phi naught, so we have to apply x equal to half of thickness, then now this phi becomes phi s and x becomes half of our thickness. So now we have seemingly quite complicated, but we have another expression. So simply speaking, so by combining these two means that relation between surface potential and midpoint potential, and another one is the N1 situation shown here. Now we can have two equations and two unknown variables, and by solving this equation numerically, we can get the correct exact value for surface potential and midpoint potential, and that is really corresponding to the charging density or integrated charge. Okay, so up to now, I have shown you the exact solution of double gate MOSFET. That is really amazing, actually, to me. It's really amazing to have an analytic expression, and that was first found or reported by Tower once again, and it was first appeared at year of 2000, so in IEEE EDL, and it has some limitations. For example, we considered intrinsic channel. There is no, how can you say, there is no doping density, mm, and yes, and that was limited to the double gate, but it was really okay. This war really initiated worldwide research activities about finding out without further analytic question for more general cases. However, uh, actually, there was no further success. So anyhow, we have to introduce some further approximations. But this one is really exact. So as much as we assume the intrinsic channel, and if a whole can be neglected, then that becomes the real solution of that problem. So in general, it is difficult to find the unanalytic expressions. So what researchers did in previous years is, okay, so intrinsic means that without any doping density, intrinsic double gate MOSFET, we have the analytic expression. How about the doped one? We don't have it exactly analytic expression. How about perfectly cylindrical structure? Unfortunately, even in this case, we have no exact analytic expression, and things becomes even more complicated if we go to quadruple one or yes. So there are many different cross sections. So among them, from our point of view, so the current currently most relevant cross section is this quadruple gate. Yes, this is a gate all around the structure with more and less rectangular shape. However, the real shape is not exactly rectangle, but corners are usually rounded. So this rounding is happening from just etching process. So this can be more or less controllable. However, we wanted to introduce smooth uh, corners to reduce the electric field clouding effect. Okay, so therefore, simply speaking, even for this simplest case, so simple double gate case, analytical its analytic expression is limited only for intrinsic case, no docking case, and if we go to more general cross sections, and then things becomes more complicated, and researchers had to introduce models for them. However, is it really effective or not? If we have a slightly different cross-section, then of course the the one obtained from different cross-section cannot be applied, then we should introduce a slightly modified model, another model. That was quite tedious stuff. And uh, so nowadays, people are not doing this stuff any further, and this solution was introduced to more general universal model for complex model. So I just took some result from my own uh, publication written by Mr. Kwang Lee. And although this one just summarizing important report, but please note that a similar attempt was initially reported uh, by December and using CMG model, the standard model for multi MOSFET adopt this model. This paper just to formulate more formal way for the model adopted in CMG. Well, anyway, the procedure is like this. Please recall our two available cases. One, planar MOSFET, and second, mm, the double gate MOSFET we have seen. What was the common procedure? First, starting from the Poisson equation and multiply or weighting factor, and the weighting factor was d5 over dx. Well, good. However, if we consider a general cross-section, for example, in this case, we are just looking at a nanosheet with a rounded corner. These corners are rounded. These corners are rounded. And in this case, what is the meaning of this d5 over dx? We have to consider two-dimensional cross-section. And how can we define the electric field like quantity? So in this paper, uh, Mr. Wang Li introduced a very good way, clever way to set the appropriate weighting factor. After that, we can just integrate this modified Poisson equation over two-dimensional cross-section. Then we can now derive on approximate relation. I'm not saying that we are exact because analytic solution is only available for those two cases, planar MOSFET and intrinsic double gate. So except for that, there is no non-analytic solution, but we can derive a good enough approximate relation. And although the notations are different and I'm not trying to follow every detail, but the result seems like this. The point is, the surface potential occurs once again, and surface potential can be written as the form of the total charge and electron charge. So of course, total charge is the sum of electron charge and depletion charge. So this number is more or less given, and we have only this electron contribution. So simply speaking, this expression gives us the relation between surface potential and electron charge, and using these relation, we can try to solve MOS equation. Then we can get once again the surface potential and inverted electron charge uh, as a solution of those uh, approach. Okay, so that is the typical one we are currently using. So although this CNC model does not follow my derivation, they have a similar expression by some intuitive inspection, but anyway, this procedure can be applied to the model derivation. So let me just conclude this discussion. Um, it is very important to understand the charge density as a function of surface temperature. However, it is not actually very straightforward. So, exact solution is only available for special cases, and for general multi-gate structure, we need more versatile and generally applicable procedure. And unfortunately, it is known to us and it is already applied to the most representative compact model. That's the reason why, even though we nowadays we have many different cross sections, by just changing the model parameters without changing the model itself, we can easily construct the charge versus gauge voltage relationship for our analysis structures. Okay, so I think that that's all for our lecture 26, and this is the last slide of our entire semester. Let me just uh, quickly comment on this year's our lecture. Uh, this lecture initiated last year. It was open or offered as a special lecture, and at that time, I just covered every detail we can deliver to our students, and the lecture progress was so slow. So in this year, I just skip many basic stuff that should be covered in the junior level course and just dive into our main content. So the main content was derivation of charge versus surface potential that was covered for planar step. After that, we have to consider Tao's double integral, and after that, now we can express some region-wide expressions for our long-term MOSFET uh, IV characteristics. After that, we have to consider short-term effect by considering two-dimensional solution of our MOSFET at the subthreshold region, and also consider various effects, important effects related to the short-term devices. So I think that the coverage is much more expanded, although the very basic steps are skipped, uh, unfortunately. But I think that it is a better direction for this course, the senior level course or graduate level course, next one. And uh, maybe in the next year, I will keep this. Direction once again, but I have a plan to changing the textbook from the towards the second edition to the newest one, third edition, and include more stuff about the double gate MOSFET. Okay, anyway, thank you for your effort during this entire semester, and see you June 16th. The June 16th will be the time, the day for our final evaluation. Thank you and bye.